Welcome back. Today is all about equality and the functions and type data types that go with it. It's a bit of a subtle topic. In fact, mathematicians today still don't quite know what equality means. We just know how to use it somewhat respectfully. So let's get started with a story problem. Imagine that I'm collecting data on some of my users, traffic to a website, some device that I have information on. I might decide to make a plot that tells me what time of day my device is being used and write down the total usage. Now, there's many people in the home that are using this device, so they lead to different threads, and these might be accumulated as averages over several days. So I can see, for example, that there's a trail of the first user in yellow here. On a different day was a different path, and so forth. Each one of these users has multiple paths. I've kept the colors the same because I know which user is which. Now, what I'd like to do is see if there's any patterns. What I notice is that two of the users end up fitting a total maximum amount used all day. It's as if they've reached their maximum usage and the software system turned off. This might be the result, for example, of parental controls and screen time limits based on the children in the home, whereas adults are allowed to just give themselves more time if they need the device to be used more often. This type of segmentation of data is very common. It's used in classification, and it's a big piece of neural network and machine learning. Try to decide which parts of data belong in different categories based on features that they seem to share in common. The lesson I want to talk about today is what this concept of in common even means. What we've said so far fits into two possible categories. We have the unsupervised users, which can use an unlimited amount of time or none at all. And we have two supervised users that once they hit a limit are now canceled for the rest of the day. If trying to organize this into logical sentences, we could start by giving names to these two categories. Drawn this way, we can see there's a lot of misleading information in here. For example, you might believe that the supervised users are simply the ones that are below some threshold. And that would make sense if this was the only picture. But we might observe a future client logs on and has different behavior. The addition of this purple client we see no longer hits that same threshold, so now we'd have the nuance. Are supervised users simply below a threshold, or are they the ones that converge to the same time usage on average? We could decide after the fact to subdivide our categories. Our machine learning algorithm might decide to add some subcategories. For example, a low usage category, which is below the threshold but doesn't converge to a common usage. This might be a grandmother who's in town for the weekend. The basic idea here is not to think of a specific problem so much as to think about the mathematics that goes behind writing down these kinds of questions. We want to think about grouping information together based on common features and separating based on differences. To write this down as an expression, we can use our first order logic. What I've written above is known as the law of the indiscernibility of identicals, or just Leibniz law for short. As a quick aside, some people would dispute whether this should go in both directions or just one. I'll be using the one direction today. The key idea here is that whenever we think of two things as becoming equal, we're saying that any property we would measure about those quantities should be the same. That is, whenever this one's true, that one's true, and vice versa. By writing it down with this logical sequence, we're able to discern what it is that our computer program is actually achieving by grouping things together. For example, if we make a category called unsupervised users, perhaps these are the category of people we want to market to. These are the decision makers, the people who have the authority to purchase things from our ads. And perhaps the supervised people will be people we prevent sending certain ads to, assuming that they might be children in the home. And perhaps low usage users would get tourism information. These would be sensible choices for a good client relationship. The contract we write up here with the Leibniz law is saying that we don't bother to think of these three yellow lines as any different. They receive the same quality of ads. Those are the unsupervised ads. Their properties are indistinguishable. Likewise, the properties of the supervised clients receive just exactly the same information. That's because we put them into categories. There's a couple of ways that mathematicians have conjured to express these ideas. The first way is the concept of equality, given by this rule. The second one is to think about taking the data and considering them as one big box full of subexamples. Here, we can take the three yellow lines as one color. Therefore, it's three parts, but also one part, the one color. The two purple lines are one color, and they've now been merged with the green line because those are both supervised users. They're two separate channels, but they're being treated the same. This is a notion of a partition. Partitions are when we make new data types comprised of the parts of the whole. In this example, the whole is all the possible lines that go on in our usage and time of day. The partition, then, is to glue together the ones that have the common properties. We could glue this together in a lot of ways. For example, our first partition is simply to observe the same colors. That's partitioning based on the user. The yellow lines are the yellow user. The green lines are the green user. Purple, the purple users. That's one type of partition. Each part can consist of multiple lines, just like any part of a data set could consist of multiple examples of that data. But there's a lot of practical nuance in stating questions like this. Classical set theory gives us a way to articulate what our concerns are in a precise enough way that we can decide what rules we want to apply to our situation. Let's clear the board and see if we can write those rules. I claim that if we stop to inspect how we've given categories to all the various data in our example, it follows these three rules. First of all, everything that we gave a category made a subset of our original set A. For example, we could have the supervised users. This would make it a subset of A because we started with the elements as being inside of A. If we want, we can articulate this entirely with symbols. We can say that script P is a subset of the power set. That means that every part in our partition will be something like this, some description of the values in A which get to be inside there. Next, we should endeavor to assign a classification to every type of data that we see, even if it means something like miscellaneous or not yet classified. Those are categories of their own, and they allow us to make sure that everything has some assignment somewhere. We write that A is in some script P. For example, we might say that every user is either supervised or unsupervised. Since we've counted every user, we know there's some part in which that is assigned. Finally, in order to make a reliable program, one that can use the classification to give the right behavior to that user, we should insist that they're not doubly classified. Otherwise, the computer might have to just guess what to assign them. So we make the rule that no A in A is assigned to more than one part of the partition. So what I have here is the symbolic way of describing the words that we had in our previous description. Part 1 says that every element in our partition is some subset of our A. Remember, 2 of the A is our power set, the set of all possible subsets. Part 2 says that if we took all the parts together and overlapped them, we would end up covering all of A. So every point is represented in some classification. Part 3 says that we're not overlapping any particular parts. If P and Q are two different parts, so they're not equal, then they will intersect with nothing in common. So they just perfectly cover the space. Many times we like to think of a Venn diagram to go with this. Suppose I think of A as looking up at this region of the sky. I can imagine that if I stare there long enough, I'll see some actual points in A, some stars. I'm not required to see all stars, I'm just figuratively imagining that the boundary A is describing some part of the set. Just like we might not see every star, a Venn diagram doesn't have to actually represent every element of a set. It's simply trying to give us a way to visualize what are some of the ways that sets can behave next to each other. Let's go through the rules of partition with Venn diagrams and see if we can understand them a little bit better. The first rule in symbols was to say that script P is a subset of 2 to the A. I remind you 2 to the A is the power set. That's a lot of notation to say what. So here what I've drawn is that my set A overlaps with another set that's in pink. We see that the pink has the opportunity for stars to exist outside. If stars exist outside, then that particular pink triangle would not be a subset of A. Some of its data is outside. By saying that the partition is a subset of the power set, we're excluding this kind of behavior. The only types of parts that we're interested in having are ones that live entirely inside the green box. For example, that triangle would be permissible. So would just an individual star and any number of things like that. The pink is excluded because it is not a subset of A. It is not in the power set. What does rule number 2 say? Rule number 2 says that no point is excluded. It says so in a rather complicated way. It suggests that we should take the parts of our partition and union them all back together. Now, because they all lie in A, when we take their union, the result will still be in A. If we took the blue triangle and the blue circle, we'd see that we haven't quite captured all of A. We have stars here and here, which have been left out. That would mean that our script T is not yet a partition. It's missing some of the data. And remember how I said that we might force this situation by including a new category such as miscellaneous. It's always possible to add more sets in order to cover the set A. Now I've guaranteed that I do cover the set A. So it's time to move on to step 3. In step 3, we see the final condition. If I take any 2 distinct parts of my partition, so they're not equal, then they should intersect trivially. That's just jargon to say they have no points in common. Let's see if that's actually happening. We see that the blue triangle here and this blue blob overlap right at that star. This means it's not yet a partition. Now we could fix this into a partition by simply creating a brand new category, the overlapping category. If we separate that out and remove those points from the other 2 sets, now we'll have a set of subsets which covers everything and has no points in common. It'll be a partition. I recommend strongly the use of Venn diagrams when getting used to partitions, but it can be overused as well, because not everything fits together as nice geometric shapes. Always remember that this star constellation idea could fool you, just like you might not see all the stars in the sky when you first look. You might not see all the points in a set when you draw a picture. You'll be more convinced by the algebraic methods and the computations that go with partitions than by merely drawing pictures. But for intuition, it's quite a useful tool. Well, now, while a partition captures many of the aspects we want out of a classification, it's not the most useful computationally. And that is because when we want to use it, we want to take a current, specific user and decide which classification they belong to. And that's not the same as going through the set theoretic rules that we have here. We don't want to look at script P so much as we want to look at the outcomes of being in one particular part of the partition. To do that calls for functions.
But for that, we will wait until next time.
That's how you take care of your chalkboard.